Hey, as part of my learning journey on machine learning, I realized I need to learn a lot of system designs. I'm very new to it, so I want to learn with you together. This is my first note on this topic. I'm trying to cover the basic elements, basically what's expected when we're talking about let's do a system design, and then the core principles of it. So let's get started. Let's start with a very simple system. I have a phone application and I want to get relevant information about the user, which is user 12 or myself. So what I do is I send a request to the web server, hey, what's the information about myself? I access it via a link, maybe api.mysite.com. Then the thing is I can't directly reach the web server from the API link. I usually need to access it through an IP address. So I went through the DNS, I sent to the DNS server what's the corresponding IP address for this URL. And then I got an IP address, I can use that. Or maybe I want it to be more than a mobile app. I want to have a service that supports both a mobile app and a web app. So what I'm doing now is I can also have a web link called web.mysite.com, and I ask this web server, can I retrieve the HTML web page? And I'll get the response. So the detailed sequence will be I first send a request to the DNS, ask what is the corresponding IP address. The DNS gave me the IP address. I use that to access the web server, and I'll get a response from the web server. As you can see, the requests usually look like something as simple as get users 12. And the response is usually looking like this. Here we say it's a JSON format with the user ID, which is part of the request as well, just confirming this is the same ID. And then we have first name, last name, and we can have nested information like address and phone numbers. We can have something equivalent to, in my opinion, Python dictionaries or lists. And let's say we have more data, so we need the help of a dedicated database. So we just add a database over here. As you can see, we have web server talking, reading, and writing updates to the database, and database returns data backward. And sometimes we may need more than just one database. Then we have a master database for distributed services, and we have slave databases that just synchronizes with master database, which is for replicates. And for users in different geographical locations, we can just have them read their closest database. And let's say the database is fine, but there are more requests, and actually we need more servers. Right now we have all the requests coming into one web server, and maybe we have more web servers, and we have a load balancer to balance requests to multiple web servers. This load balancer, of course, can balance load. You can direct the user to their closest web server, or maybe this web server is down for some reason, and it's just directing all the requests to the working web server. That also makes the system more robust. So this is the system we have right now. It looks like this. Sometimes we think we can actually relieve the load of the databases by including caches. For example, the static information. For example, when some information hasn't changed, we can just put it in a cache such that we don't have to query the database every time. And in fact, something that often shows up in the modern application is something called CDN, or Content Delivery Network. CDN stands for Content Delivery Network. There are a lot of services, let's say AWS, and what it does is when a request comes, instead of going to the server load balancer directly, it went to the CDN, and maybe it says, well, you know what, I already have the information cached over here, and I can deliver it to you directly, or I don't, so I'm going to go do the usual process and then return the information, but cache it for the use for next time. CDN is managed by someone else, usually a third party, and usually they are very fast, they are very distributed, such that different users can get their local, regional servers to respond rather than your server, which might be far away from where the user is. And of course, there are other countless components to consider in a system design problem. For example, there are message queues. if there's a producer consumer and we want them to synchronize in a asynchronous fashion, and we just publish all the tasks we need to do in a message queue, and whenever the consumer is ready, it'll just start consuming the message queue in a first in, first out manner. For example, if we are trying to process some photos, the web servers just send as requests in a queue, and whenever the photo processing workers have availability, it just consumes from the queue in a first in, first out manner. And of course, in a system, there's also logging, metrics, automation. It needs to be multi-level such that we can use those to identify problems in the system. And we can do logging at the host level, like CPU, memory, I/O, whether it's saturating or too low. Or we can have aggregated information, for example, the whole database tier or the cache tier performance. Or it could be just business related, like daily active users, retention for a user, or even the revenue. And a lot of those can actually be automated for scalability. So this is, with all the components, we talk about what, let's say, a modern, relatively simple sales system can look like. And that's what we need to do in the system design process. We have the user, and we're querying the API. We have some client requests over here, and it hits the application code. Then it depends on what we're asking. If it's just a simple read, we can check if the data is cached. If it's cached, great, we just read the cache. And if the cache misses, or we're trying to write something, then it goes to the database. The database, of course, will reply to the application code what the data we want is, and of course, it'll update or invalidate the cache, because next time the cache can be used. Or maybe we need to apply updates to the search index because something has changed, and then the search request can come over here to use a full text index to find the information we need in a very fast and systematic manner. Sometimes the request is a synchronous task that takes a while, let's say processing of a photo, let's say. And then we have a message queue to queue those messages. We have application code, and application code can then, when they're available, they can deal with the tasks such as I send an email and then send it to the outside world. So this is what we're talking about when we're talking about we're doing a system design. So what kind of principles can we use to design a good high-quality system? From the book, Designing Data-Intensive Applications, or DDIA, I love in the first chapter how they laid out 3 principles: the reliability, the scalability, and the maintainability. Let's see what each of it means. First of all, reliability. Reliability means the software can perform correctly. By that, I mean not only have the right output, but also at a reasonable performance, but also robustly, even in case of adversariety. So that would have 4 dimensions. The first dimension is functionality, means that it does what we expect it to do at a reasonable performance. And also usability, which means even if there are some faults, either hardware or user, it can still function. Or performance, which means that it needs not only to function, but also to return the results at a reasonable latency or response time. And the last, security, which means it can withstand either abuse or unauthorized access. All those system faults may come from, in general, 3 different categories. It could come from hardware faults. For example, hard disks may fail. I've faced that a few times in my career. There might be a network outage, or just someone accidentally unplugged the net cable. Or it could be a temporary power loss for one machine or a group of machines. It could also be software errors. For example, there could be bugs. Or there could be a runaway process that just kept consuming resources, causing out of memory or out of disk space. Or it could be a cascading failure that some nodes in the whole system is starting to behave unexpectedly, and the whole system cascades the mistake and then shuts down. Or it could simply be from a human error. It could be a misconfiguration by the operator. It could be accidentally deleted by someone else. Or it's just simply an incorrect deployment by the person who's deploying this application. And within all those three dimensions, we can decide to make the system a little bit fault resistant by doing the following. For example, for hardware faults, we can add redundancy. If we have multiple machines, even if one of them is shut down, maybe we can use something like the load balancer that's just to shift other things to other still operating machines. Or we can have automated failover as part of what I mentioned instead of doing it manually, and we can do regular maintenance to minimize the chance of hardware faults. For software errors, first of all, we can carefully think through and design the system, making sure are the assumptions we're making when designing the system really true, and how do they interact? Can we minimize the unnecessary coupling for the complexity? Of course, we can thoroughly test the software to minimize software error, and sometimes we may actually allow crash and have the system restart. Or in fact, sometimes we can even manually trigger some of the crashes to make sure the system is running, and then make sure the system is robust, that we have our failover mechanisms. And of course, we can always monitor to make sure that those software errors are happening immediately, and then we just fix it. Of course, there's human errors. Human errors can also be similar to software errors. It can also be mitigated by careful design. The workflow, the usability is high, then chances of software errors low. In the testing, we also test the human in the loop. And we can create separate environments like a sandbox such that when we're testing something, we don't have to test the whole operating system, the whole system that we are operating upon. And we can have an easy rollback mechanism. If someone misconfigures something and caused a system shutdown, we can always roll back to the previous configuration to have it continue to run. Of course, monitoring always helps. And in general, good managerial practice, because we're managing human over here, can also help. So that is reliability. Let's focus on the second dimension, scalability. Note that scalability is not simply as something is scalable and something else is not. It's not a one-dimensional topic. It depends on which exactly your application is and what exact load metric are you talking about. Are we optimizing for queries per second? Are we optimizing for read and write? Are they symmetric? Is the ratio 50-50? Or are we optimizing for the peak, let's say, user numbers within a session? If you're saying different things are different bottlenecks for your application, then it's important to decide which one are you optimizing for. On a good case, you're just wasting time. On a bad case, sometimes optimizing on the wrong metric can get you further from where you want to go. I think one great example to show this is an example from Twitter that the author of DDIA mentioned in the book. I think all of us probably use Twitter now, X, right? I follow a lot of people, and whenever they send a tweet, because I follow them, my home feed is just a collection of what they posted. Let's say it's just simple chronological orders without any optimization or recommendation systems. And there are two ways to do this. I think initially Twitter did this method one, where it says, well, all the Twitter is a huge table of all tweets under the sun. And because I'm logging in, I need to access my home feed. And this is my follower ID. I just look up, who do I follow? Maybe I follow user number 12, and therefore I just look up user number 12, name and profile image. I add that to my home feed because I need that. And that person said this tweet, just setting up my Twitter. And there's a timestamp of that. So I just query the whole database by filtering what I need every time. So this works fine, except for one problem. You probably already realized that there are way more times that a user is actually looking at its home feed than the number of times where people are tweeting information. Reading is easier than me sending something, creating something, and then publishing it, right? So quickly, the server is overloaded by this method. So they say, well, you know what? Maybe we can do method number 2, where a user posts tweet, and that's relatively infrequent, right? And for all the tweets, it's just like sending an email. I'm just sending an email, a message to different recipients who subscribe to me. And by this way, I only trigger this message queue whenever people tweeted something, and this is usually we call the fan out process, right? We spread the information out. So this seems to be doable. But there's also an issue over here. There are actually quite some people that are celebrities, and they have a huge number of followers. Whenever they say something, even if they just like a 4.6K or writes per second, because they have a lot of followers, let's say up to 31 million, they can have a lot of writes in the system, and the system is also overwhelmed. So this shows that different systems have different advantages, and it optimizes for different kind of scenarios. For one scenario, the top method is better. For some scenarios, the second method is actually better. So in case you're curious, actually later Twitter adopted a method that's a hybrid of the two. For the people who has a very high number of followers, they use the second method. Sorry, they use the first method because the second method doesn't work. And for the majority of people, they use the second method, and that worked out fine. It is common that we need to quantify the metric of a load and performance such that we can optimize on top of it. And there are a few notes I want to mention. One is that it's simple just to say, hey, this is the average response time for a request. This works, but this may hide a lot of information because what you care is not one average number, but the whole distribution. Maybe, for example, in Amazon, there are a lot of users who buy a lot from the Amazon.com website, and those users actually have a lot of data to transfer, and therefore they are the slower one. You want to make sure they are taken care of, but if you use the average metric, maybe that's masked. So one very common metric that we use is the percentiles. If you find out the 99th percentile or 95th percentile or something, average or median is just the median is simply the 50th percentile rate. This actually is better. It's more common nowadays when we're describing a system metric. We're talking about 99th or 99.9th percentile, and as long as that percentile is fast enough, we can accept the system. This is actually a great example, also mentioned in the DDIA book. The other thing we want to know is, notice that there are sometimes a lot of things we can parallel run, right? We have a web application and we have 7 backends down there. You can notice that there are sometimes things are finishing very fast. For example, this server finishes things at the 76 millisecond, which is pretty fast. But sometimes there's just some backend that's critical and that takes longer than it takes. And therefore, the whole end-to-end user response time is very long. It's the 487 because it has to wait for every thread to finish or every process to finish before it continues. So just to note that sometimes just a few of those bottlenecks can make the system really slow. So please don't simply average all those out. When you're measuring things, don't measuring things, serially. Make sure you test the system as it's going to be tested or used in the real production time. When we are coping with high load, there are different methods. The dichotomy people usually talk about is the vertical scaling, which just means getting a beefier and beefier server computer that you can have. You can make the CPU better, you can make the RAM bigger, you can have a hotter disk, faster disk, etc. It's simpler as you can imagine, which is to a hardware upgrade, and that's done. Recently, there's more and more horizontal scaling because it's very easy to hit a bottleneck of how better you can scale vertically, but horizontally you can almost indefinitely scale your system, right? Just adding more servers to it and share the load. It's more complicated as you need to manage how they share, but this is usual dichotomy. And note that if something is stateful, for example, a master database, it's sometimes easier to do the vertical scaling. I think recently maybe there are methods to deal with this, but usually if you want to go simple, it's much easier to scale the stateless processes in the horizontal scaling because it's trivial, just share it or distribute it. But for vertical scaling, if it's stateful, vertical makes it easier. And also for scaling, there's also this manual versus elastic if it's horizontal scaling. For example, if you see that the machines are being saturated, then you can manually increase, of course, but you can also have the system to notice if the pressure is above 80%, then you need to elastically spin up a few more instances and have it share the load. So that's scalability. The third one we haven't talked about yet is the maintainability. About maintainability, It also has three aspects: operability, simplicity, and evolvability. Let's talk about them one by one. The first one is operability. So a good team that operates well need to do the following things. They need to be able to monitor the system, and whenever it's going wrong, we can restore it quickly. Or when there's a problem that happens, we can quickly perform the root cause analysis to find out where the problem is. And when there's no issues happening, the team can update the system, patch the system, and manage all the dependencies. And of course, there's knowledge management of how to do these such that when people leave, new people join, they can share this document, this message, instead of keeping it as tribal knowledge. And how do we help them from the system side? The system can help them by, for example, adding visibility into the runtime and the internals to help them monitor. The team can have existing automation tools and integration tools that's easier to use such that they don't make mistakes in using those tools. And we can also carefully design the system to avoid the unnecessary dependency between individual machines or even components. We can provide good documentation. The system maybe can even have some self-healing functionality. Or still, when we even have the self-healing functionality, we can add manual control to it. And it should also have good default and predictable behaviors. The second one is simplicity. If the system is overly complex, then we've seen problems of explosion of state spaces that is overly complicated beyond a way that's manageable. We have tight coupling of nodules, such as you turn one knob, everything changes. We have tangled dependencies. If you upgrade one component, the whole system crashes without easy ways to fix it. There's inconsistent naming. There's one variable called this in this place and the other called the other. And unless you go into the code base, it's hard to figure out whether they're the same or different. And there are a lot of special cases that you need to do if-else conditions to deal with. And a good way to deal with the simplicity or the unnecessary complexity issue is by using good abstractions. Good abstractions means we can hide those details under the table and just expose the user and maintainer and the programmers an easy, clean, and simple facade that they can operate on. It's making the system even usable for a wider range of different applications if later want to extend the whole system. We've seen great abstractions. For example, all the programming languages, you're using CPUs, you're using memories, but you're not using the low-level assembly language. You're using higher-level programming language like C and Python and C++. Similar SQL. It's a data query language that it hides all the very complicated, even distributed systems behind it, and it just gives you a clean interface. You just need to worry about which data, which column do you need to query from which term, from which table, and how do we join those together. And the last is evolvability. We all know that things evolve. The requirements from the use case and priorities may change. Users have different needs. Business may need to go to a different direction as time goes on. Or the application user doesn't change, but the regulatory department suddenly said, we have this new requirement for this new AI application, and we need to do changes. Or we've been using a platform, and that platform changed. And sometimes it's just a natural growth of the system that making us realize that we have to change our architecture to make it fit. And there are approaches that can help with this from the system point of view. Agile development is a method we often know, although most of it is used for smaller applications. It's very helpful in general, and there's other methods like test-driven development. And if we design carefully on the system to make sure it's as simple as possible without unnecessary coupling, and we have modular designs, it'll help things. So that's my notes for the initial video on the basic elements and what the principles are. I've been mainly referring, as I've been citing across the slides, the System Design Interview and Insider's Guide by Alex Xu, and also the Designing Data-Intensive Applications from Martin Kleppmann. So that's it for the first video. Thank you for your time. If you have any questions, please let me know in the comment section. Thank you very much.